What is convection? Convection is involved fluid motion as well as heat conduction. It is a mode of heat transfer between a solid or liquid surface and its adjacent liquid or gas that is in bulk volume. For convection heat transfer, we use Newton's law of cooling. To clarify more on this topic, we will look at the figure 6.1. When there is no fluid motion, the energy of the hotter fluid molecules near the hot plate is transferred to the adjacent cooler fluid molecules. Heat convection depends on several fluid properties such as dynamic viscosity, thermal conductivity, density, specific heat, and velocity. There are two types of convection, which is forced convection and natural convection. Forced convection is when the fluid is forced to flow over the surface by external means such as fan, pump, or wing. For natural convection, it is when fluid flow caused by buoyancy forces that are induced by density differences due to variation of temperature of the fluid. Nusselt number. Nusselt number is a dimensionless number. It is also viewed as the dimensionless convection heat transfer coefficient. Number also represents the enhancement of heat transfer through a fluid layer as a result of convection relative to conduction across the same fluid layer. Thermal boundary layer. Thermal boundary layer is the region in which the fluid velocity varies from 0 to 0.99 V. It is developed when a fluid at a specific temperature flows over a surface that is at a different temperature. Besides that, we also have velocity boundary layer. Velocity boundary layer is developed when a fluid at uniform velocity approaching a plate. As we can see the figure above, the region of the flow above the plate bound by delta in which the effects of the viscous shearing forces caused by fluid viscosity are felt. For thermal boundary layer, we have two formula, which is Reynolds number and Prandtl number.
Let's take a look at this overview on external and internal force convection. External force convection is a convection whereby the boundary layer develops freely without any constraints, compared to fluid that is confined by a surface in internals. There are two cases under external force convection that are parallel flow over flat plate and flow over sphere and cylinder. There are three important equations in this topic, which are boundary layer equation, friction coefficient equation, and Nusselt number equation. Each equation are applied differently based on the flow regime, which are laminar and turbulent flow. The equations are further divided into local and average. The equation also take into consideration flow condition when both flow regimes exist together, whereby, due to the length of plate, the flow is turbulent enough but not enough to neglect the laminar flow. To make up for fluid with different Prandtl number, for example liquid metal like mercury, a Nusselt number correlation is formed, which is looking into the effect of roughness. Drag is a force exerted on a body by a flowing fluid in the direction of fluid flow. For a streamlined body, rougher surface increase drag, but for blunt bodies such as cylinder and sphere, surface roughness decreases drag. There are two types of drag, which are friction drag and also pressure drag. And these drag characteristics is defined by the equation drag coefficient. In this topic, fluid properties are evaluated using the film temperature equation. In external force convection, transition of fluid flow from laminar to turbulent is affected by many factors and best represented through the Reynolds number. Based on engineering analysis, the external force convection Reynolds number is defined as: looking into internal force convection, flow in tubes can be laminar or turbulent. For flow in circular tube, Reynolds number is defined by the equation. For non-circular tubes, friction coefficient, Nusselt number, and Reynolds number are based on the hydraulic diameter dH. At the entrance region, there are two types of boundary layers, thermal and velocity, also known as hydrodynamic. Both can be dissected into two regions respectively, which is the entrance region and the fully developed region. The entry line for laminar flow in tubes can be obtained from two correlations. Entry line for turbulent flow is shorter compared to that of laminar and become less dependent of the Reynolds number.
Moving on to the next topic, which is the heat flow through tube from one fluid to another. We can classify the flow of a fluid in a cylindrical tube into either a laminar or a turbulent flow. So assume that it is a fully developed incompressible Newtonian steady flow conditions. So when we want to define whether the flow is either laminar or turbulent, we need to define the Reynolds number. Now the Reynolds number is given by the formula of inertial forces divided by the viscous forces, as you can see here. So on what number does the Reynolds number need to be to consider it into laminar or turbulent? So when the Reynolds number is in the range between 2300 and 4000, it is a laminar flow. Higher than 4000, it is regarded as a turbulent flow. Heat transfer correlations based on experimental results are typically divided into those applicable in the thermal entrance regions and those that apply in the fully developed region. So in the case of laminar flow, it is important that we are aware of this distinction, and normally a laminar flow heat exchanger is designed to be short to take advantage of relatively high heat transfer rates that are only achievable in the thermal entrance region. So when predicting heat transfer rates in the laminar flow, it is important for us to analyze the Nusselt number in the entrance region. And as you can see from this image, there are a few correlations that can be taken into effect. The first two, that was by Edward et al. And Cedar and Tate in 1936, is for the circular tube laminar flow. And the third one, the Nusselt number, is used for the parallel plates. Moving on to the turbulent flow in tubes, there are a few additional mechanisms, and this additional mechanism is commonly termed as eddy transport. It is an intense, providing much better transfer of energy across the flow at a given axial position than in laminar flow. Another thing in turbulent flow is that the extent of the thermal entrance region is relatively short than laminar flow, whereas it tends to be longer. The flow in these tubes can be classified into two, which is the smooth tubes and also the rough surfaces. In turbulent flow tubes, we need to take note of the friction factors in the smooth tubes and also in the rough surfaces, because it can give a very different effect from the Reynolds number to the Nusselt number. And there are also a few correlations that can be taken into effect. As the smooth tubes, there are a few more correlations. As you can see here is the Chilton and Corbett analogy, and also Corbett equation for fully developed turbulent flow in smooth tubes. And there are just two. A few of these correlations can give a more accurate Nusselt number than other correlations, so we can choose whichever one we need to use. For fully developed turbulent flow with rough surfaces, we need to use the Corbett equation, and the friction factor can be easily accessed via the body chart.